Hello everyone. Am I audible?
Yes,
Okay, so we have started discussing orthogonal factor model yesterday. So today also we'll continue with the same thing. Any doubt in whatever we did yesterday? No doubt?
Hello, ma'am.
Yes.
Yes, ma'am. Previously, as we have found the F matrix and the Q matrix based on the model which we considered without the specific factors. Now we will be finding out those Q, F, and the U vector based on this the model assumption we have made using these specific factors, right?
Yes. Actually, the previous thing we did not have specific factors because we had assumed that only k eigenvalues are positive. Only k eigenvalues of sigma matrix are positive and everything else is zero. That's what we had assumed. So we could find factors f and we could get q. But now we are not going to assume that the remaining eigenvalues are zero. So they can also be positive. And as I mentioned, in that scenario, actually it is not possible to get a unique solution. So we are going to get an approximate solution. Okay. So in fact, we won't get f directly, we won't get u at all. We will try to approximate f and we'll try to get specific variances. Okay. So let me start with some properties of orthogonal factor model. Let me share my screen. Okay, can you see the screen?
Yes, ma'am.
Okay, so now we will be studying some properties of orthogonal factor model. So first of all, how do we interpret factors? Okay. By the way, so far we have not discussed how to get these Q, F, etc. Okay. So far we have not discussed that. We will study that in estimation in factor model. But currently we are just trying to understand the orthogonal factor model from all the angles. Okay. So first thing towards that is interpretation of factors. So how do I interpret the factors that I have? F. Because we said that, okay, we might, like, when do we do factor analysis? When we have some latent factors which we are interested in at the back of our mind. But then in my mind, I would have some list. It is not necessary that data would give me exactly those factors. And in fact, even if the data set does give me factors in that order, does give me those factors, it still need not be in the same order. Okay. So we need a way to interpret the factors and to give them names. So for that, what we are going to do is we are going to compute correlation of factors with original variables, because we saw in the introductory lecture that I would have x1 x2 xp as my observed variable, and then f1 f2 there we used y, but now that we know they are factors, so I can call them f1 f2 fk. And we saw that there are connections between them, so each x may be controlled by something, few of these factors, or you can say other way around, every f controls few of these xi's, etc. So if I know that, okay, say these xi's are being controlled by this particular f, then I can give some name to this f. For example, if I go to the IQ thing again, if suppose this is linguistic test score, okay, then this is suppose reasoning score, okay. Something is wrong. Okay. Anyway, so in that case, if say factor 1 is talking about linguistic as well as reasoning both, then I can say that okay, factor 1 probably is related to language related thinking abilities, because you need reasoning skills as well as you need language related skills. Okay. So yeah, there is something wrong with my let me close and open it again, because it is writing on its own without me doing anything. Let me see if it is fixed. No, it is still writing in air. Okay. So and I cannot even erase this stuff. It's yeah, okay, fine. Is it okay? So uh, we need to see what is the relationship between each x and each f, so that we can give better meaning to the factors, better interpretation to the factors. Okay. So I want to compute correlation between xi's and fj's. Okay, that is my objective here. Okay, I want to compute correlation between xi's and fj's. So how do I do that? Let me first compute covariance between the vector x and the vector f, because we want all possible correlations. So covariance between x and f, it would be expectation of x minus mu into f prime. Am I right? Because f had zero mean as per our assumption. So it would be expectation of x minus mu into f prime. Everyone with me so far?
Yes, ma'am.
Okay. So what would this be? It would be expectation of x minus mu f prime, which I could write as expectation of xf prime minus mu f prime. Or is there any other way in which I can simplify this? So what I know about my factor model is x minus mu is equal to qf plus u. Correct? This is my orthogonal factor model. So using these, can I say something about this? So what I can do is I can substitute for x minus mu in terms of qf plus u. Okay, so I won't need this simplification then. So if I write this as qf plus u and then f prime as it is, so that I have ff prime and I can say something about that, and I know something about uf prime also. I don't know anything about xf prime because that is what I'm trying to find. So this would be expectation of q f f prime plus uf prime. So this would be q expectation of ff prime q into expectation of ff prime expectation of ff prime plus expectation of uf prime, because u is also random whereas q is constant. And we saw yesterday that expectation of ff prime is an identity matrix, so it's just I, and expectation of uf prime is 0, because this is again our assumption that covariance between u and f is 0. Okay, so what I got is covariance between x and f is Q matrix, and from this now I have to compute correlation between x and f. I did give you some homework in the introductory lecture, so maybe very first technical lecture, how to compute correlation from covariance matrix. I think I had asked you to give matrix representation. So if I do that here, I need to construct a diagonal matrix d raised to minus half q. From where does this come? So D is a matrix whose diagonal entries are sigma 1 1, sigma 2 2, up to sigma pp, which are nothing but variances of individual xi's. What I have done and why I have done it. Okay. So in general, we know correlation between any x and y in the univariate setup would be covariance xy upon square root of variance of x, variance of y. So if I go for multivariate setup, what I have to do is say dx be diagonal matrix where diagonal entries are variances of components of x, and dy be the diagonal matrix where diagonal entries are variances of components of y. Then dx raised to minus half would kind of do this role of square root of variance x in the denominator. Similarly, dy raised to minus half would do the role of square root of variance of y in the denominator. And in between, I will have the covariance. Okay, whatever is covariance matrix between x, y. Okay. I cannot have dx raised to minus half, dy raised to minus half together because the orders may not be compatible. So if x is of order say p cross 1 and y is of order say k cross 1, then dx is p cross p, this is p cross k, and then this is k cross k. So the orders are compatible. Is it okay? If I have dy dx both on one side, then the matrix product won't be possible. Hence, we have to have d raised to minus half q into here diagonal matrix with diagonal entries as variances of f, which we know is I. So we don't need anything here. Is it okay? So correlation between original variables, I mean correlation between the observed variables and the common factors is basically some scaled version of the loading matrix. Okay. Hence, loading matrix has a lot of importance because loading matrix is going to tell me what is the role of every factor in every variable. Is it okay up to this? Everyone is following from here to here because up to here it was just a simple derivation, but covariance to correlation, is everyone clear with this part?
Yes, ma'am.
Okay. So factors would be interpreted via the entries in the loading matrix when they are scaled with the help of variances. Okay, so this is going to be useful in interpretation of factors. Now there is another important property of orthogonal factor model, and that is known as invariance of scale. So whenever we learn any new such things, we generally talk about shifting of origin and shifting of scale. When you learn, say, raw moments, central moments, etc., in fact, covariance, correlation, etc., at all those time points, you talked about whether the things are scale invariant. Okay, so same thing we are going to do here. Now, let x be my original observed vector. Okay, so these are my observed variables, and let y be a scaled version of x where C is again a diagonal matrix with entries C1, C2 up to CP. First of all, is it the type of scaling that we want? So for example, if I want to change units of x, can it be done through this? So let us try. So suppose x1 is say height in say centimeters, and x2 is say weight in kilograms. Okay, and now I want y1 to be the same height but recorded in meters, and I want y2 to be same weight but I want it to be recorded in grams. Okay, then what do you do? So we know relationships between x1 y1. So y1 would be x1 upon 100, and y2 would be x2 into 1000. Am I right? So can I say that y1, y2 is basically 1 by 100 and then 1000 0 times x1, x2? We have to check. Because if that is the case, then yes, change of unit is taken care of by whatever we are going to do now. Okay, so this will be 1 by 100 into x1 plus 0 x2. So this will be 1 by 100 into x1 and then 0 x1 plus 1000 x2, which is what we want. Okay, this is exactly what we want. We want y1 to be 1 by 100 x1 and y2 to be 1000 x2. Okay, this is x, this is not y. Okay. Okay, so if we want to scale the variables by some constant, then yes, this is a way to do it in a matrix notation. Y equal to Cx, where C is a diagonal matrix. Now what happens if I do orthogonal factor analysis on Y instead of X? Because see, when you carry out any such exercise, you can choose to work in any units, and ideally your results should not be affected by the units that you are working with. Okay, so let us now first compute variance covariance matrix for Y. Okay, so variance covariance matrix for Y would be sigma Y. So it would be variance of Cx because Y is Cx. So from the theory that we have learned, it would be C sigma x C prime. Correct? C sigma x C prime. Okay so far? Now,
Yes, ma'am.
okay. So now what we know is we can now try to have a an orthogonal factor model for y also, just like we had for x, and we want to see whether there is some sort of equivalence in these models. So for x, what I have is x minus mu is equal to qf plus u. Let me write x everywhere just to indicate that this q is based on x, this f is based on x, and so on. Okay, so this mu x also I will write. Okay, so we have seen yesterday that this gives rise to sigma x as qx prime plus psi x. Am I right? Sigma is qq prime plus psi. This is what we derived. Now, what if I want to do something similar for y? So what we know is y is cx. So expectation of y would be c mu. So let me try to multiply this equation 1 by c. So I would have c x minus mu is equal to c q f plus c u. Okay so far? So what does this mean? This would become cx minus c mu
Yes, ma'am.
is equal to c qx fx plus c ux, and now my cx is y, c mu is mu y, correct? So this, so can I possibly call this as qy as cx? Fx remains as it is, and now can I possibly call this as uy? Okay, because c is of order p cross p, this is of order p cross 1, so it's okay. Okay, so what is happening is I am actually getting same factors. Got it? Same common factors. The loading matrix changes, the specific factors change, but the common factors remain the same. Okay, I don't have a different fy here. So it means that the common factors remain invariant under the change of scale. But we need to see what happens to sigma y also. So sigma y would be expectation of y minus mu y prime. So this would be qy plus uy into qy plus uy whole prime. So this would be expectation of qy plus uy. Then prime of this would be fx prime qy prime plus uy prime. So this would be qy fx prime qy prime plus qy fx uy prime plus uy fx prime uy prime plus uy prime. Okay, so sigma y would be qy. Expectation of fx prime we know is identity matrix, so it would be simply qy prime plus qy expectation of fx uy prime. Let me substitute. Uy prime is c ux whole prime, correct? Plus again c ux whole prime fx prime expectation of all these things qy prime plus expectation of, again let me substitute, cux whole prime. Okay, everyone with me so far? Anyone with me so far?
Can you explain this last step again?
Yes, ma'am.
Okay. What I have done is I have just substituted values of qy and uy, because here see, we had called cqx as qy and we had called cux as uy. Okay, so I'm just substituting those
Yes.
things, nothing else. So wherever I had qy, I will, okay, qy anyway I have kept it as it is, but this uy I have made it cux. Why did I do this? Because I know relationship between fx and ux, but I don't know relationship between x and uy as of now. Okay, is it okay? Whoever
Yes,
I
ma'am.
asked.
Yeah,
Yes.
ma'am. The third thing, expectation of like, see, here we have put that expectation of uy and fx
Oh,
prime and
sorry.
qy
This
prime.
shouldn't be prime. This
Yeah,
shouldn't be prime. Yeah.
yeah.
I'm sorry. I'm sorry. Thanks. This shouldn't be prime. You're right. That was the only problem?
Yes, yes.
Okay. Okay. So I have qy prime. Of course, I have to expand this also, but as of now, let it be as it is. Qy. Now, this is going to be cux prime would be ux prime c, and c is again a matrix of constants because it's like a scaling matrix. So I would have expectation of fu, c would be outside, expectation of fu prime, c would be outside, and expectation of fu prime we know it's 0, so this whole thing is 0. Same story here, and I'll be left with expectation of c ux prime c prime. So I have, now let me substitute qy. Qy is c qx. This with prime, it would become qx prime c prime plus, in between things are 0, and then c expectation of ux prime c prime. So this is c qx prime c prime plus c, this we know is psi c prime, correct? Expectation of ux prime is variance of u, and variance of u we know is psi. So this is c qx prime plus psi x c prime, and we know qx prime plus psi is nothing but sigma x. Okay, so of course we knew this because y is cx, so sigma y would be this. But in the process, what we have learned is that the loading matrix, so qy is just cqx, and psi y is just c psi x c prime. That's all we need to emphasize. Okay, we have already seen that the invariance is there, fx remains fy, so the factors don't change. The loading matrix does get changed, and this also gets changed, specific variance matrix. And we also need to see what happens to the relationships between original variables and the factors in both the setup. So we have already computed covariance between, correlation also, correlation between x and f, and we have found out that that would be dx raised to minus half qx. If I try to find correlation between y and f, okay, so it would be dy raised to minus half, and qx we know is now has to be replaced by qy. So qy is c qx, and what do I know about dy? Can I say it is c dx, or is it c something else dx? Is the question clear? What is the relationship between dy and dx if y is equal to cx?
Uh, it is dy is equal to c square into dx.
Sorry?
Uh, c square into dx.
Okay, we will need something like c square into dx, but the problem is c is a matrix, so I can't really
Yes,
say
ma'am.
c square.
Ma'am, it will be ma'am, it will be C dx C
Correct. It will be
transpose.
c dx c transpose. Those of you who are not convinced, please go back to the example that we had, height and weight, and try to convince yourself by solving this. Okay, dy would be c dx c prime. So dy raised to minus half, when I compute, what would it be?
Ma'am, C transpose in C transpose inverse dx inverse C
C
transpose.
transpose inverse dx inverse.
Actually, that will be
I want minus half. Inverse would be this,
uh,
correct?
yes, ma'am.
Inverse would be this, but I need by 2. So should I simply make this by 2, by 2, by 2? Means, is it this? I don't know, I'm asking.
Yes, ma'am. It will do actually. It will
It
work.
will be this one? Okay, this is a homework. Check whether this is correct. Okay, check whether this is correct. This is homework for all of
Okay,
you.
ma'am.
Uh,
Okay, today I'm going
Madam,
to assume it is correct because nobody is contradicting me. I mean, nobody is
hello.
contradicting whatever Kushal said. Kushal, right? Yeah.
Yes, ma'am. Yes, ma'am. Well, actually, it will do
No, no, no.
because
I don't
that
want.
will
I don't
that
want.
particular
Wait,
thing
wait,
will
wait. I don't want explanation right now. I want people to think about it.
Also,
If you give
madam,
explanation right now, nobody is going to think about it later. So I don't want to you
sure.
to explain it right now. Everyone should think about it and prove that this is true or prove that this is not true. Either way is fine. And if you end up proving it is not true, let me know.
hello, madam.
Yes,
Madam,
not now.
here,
If you are
uh,
going to discuss answer of this, I don't want it now.
no, not answer.
Yeah,
I just want to confirm that C and C dash will be same, right?
correct. C and C prime will be same because C is a diagonal matrix. Okay. So yes, so dy raised to minus half. I'm going to listen to whatever these people are saying and substitute this. If it is wrong, we'll have to do this derive again. We will have to do this derivation again. So c raised to minus half, dx raised to minus half, c raised to minus half. So c raised to, sorry, there is no x in c. C raised to minus half, dx raised to minus half, c raised to minus half, cq is there. So this becomes c raised to minus half, dx raised to minus half, c raised to plus half, qx. Am I right? So
Yes,
this
ma'am.
would be c raised to minus half, dx raised to minus half. What do I know about c raised to half qx? Do I know anything about this? No, I don't know anything about this. So I'll keep it as it is, c raised to half qx. Can I somehow relate this to correlation between x and f? That is our question. Correlation between x and f we know is dx raised to minus half qx. So can we somehow bring that in? Yes, anything? Can I relate correlation between y and f to correlation between x and f? If we are stuck here, we can start that way also. I mean, if someone feels that starting from x would be easier, we can do that also. I don't mind. Or did we do some mistake here in the homework part? Okay, so
Ma'am,
now,
I think the homework part is wrong over there since we are not getting a right perform over here.
okay, so now this you have an additional homework now. Okay, because it's third week, so third week is finishing. This is Saturday, so it's high time that you guys start working independently. So now this is also homework. Okay, this is also homework. Completing whatever is incomplete here and then working this out. Okay. So that's why you should talk fast in the class. Now that you have delayed it, your homework has increased. So homework is figure out relationship between correlation of xf and correlation of yf. Okay. F is same at both the places. Okay, and for that you are going to need this, which you'll do. Okay. Okay, so this is okay. Let me move to the next part. Do we have time, or 12:54? Okay, let me take for some more time. So now what we've been doing is, basically we said that factor analysis is also one way of reducing dimension. Okay, so we want number of factors to be less than number of observed variables, that is for sure. And I also mentioned at that time that factor analysis has another philosophical difference with PCA, that the factor loadings are not unique. There is no, first of all, there is no unique solution. You can rotate to get different solutions. So how does that happen? So if I have the orthogonal factor model as x equal to qf plus u plus mu, this is one solution. So here, this particular choice of q and f is going to provide me one solution. But I can bring in some orthogonal matrix here. So I'll have q, g, g prime, f plus u plus mu. Why am I saying that G should be orthogonal? Because then only GG prime would be identity. Okay. If GG prime is identity, then only I can bring it here. Otherwise, I cannot simply change right hand side and keep left hand side intact. Okay. So G is some orthogonal matrix of appropriate order. What should be the order of G? What should be the order of G? What is the order of Q? P cross K. F is K cross 1. So what should be order of G?
K cross
Ma'am,
K.
K cross K.
K cross K. Okay. So GG prime is I. So I'm not changing the equation. So I can do this. And now, see, I can club it in a slightly different way. So I'll take QG as here and then G prime F as here. So this is now rotated version of original F. I can call it as FR. So rotated F. And this I will call as QR, rotated Q. So rotated version of F, because multiplication by an orthogonal matrix gives rise to rotation. Rotated version of Q. And this is still a solution because now X is equal to this new Q into new F plus U plus mu remains as it is. So this is still a solution. So by rotating, I am getting a different solution. Is it okay? Hence, factor loadings are not unique because loadings are changing by rotation. And of course, factor scores would also change by rotation. We have not yet defined factor scores, so forget about it. But I do have another question here for you. I said we need an orthogonal matrix so that GG prime is I, so that we are not changing this. But why orthogonal? Can I have some other non-singular matrix, means matrix whose inverse exists, and can I make it say HH prime here? Okay, so can I have say H inverse? I can't have prime if it is not orthogonal. So instead of this GG prime, can I insert some non-singular matrix H of order K cross K and take its inverse H inverse, so that the right hand side of my equation is still okay because HH inverse is I. And then can I make my rotated version of Q as QH and rotated version of factors as H inverse F? Is it possible, or does it have to be orthogonal matrix? This is my question. Why to stick to orthogonal matrix? Why not take any non-singular matrix and its inverse? Is the question clear?
Yes, ma'am. Ma'am, providing an orthogonal matrix is like providing a just a direction for the rotation. It won't change
Okay.
the complete equation. Like taking H and H inverse, which are only non-singular, it
Hmm.
would change the complete angles between Q and F in that case.
Fine. What is the problem if I change angle? If I'm
Ma'am,
okay
then,
with changing the angle, then
ma'am, but it won't be your actual analysis that you were going for. It,
no, why not? See, mathematically it is still matching. Mathematically, I have not changed my equation. I am putting HH inverse, which is I. So I have not mathematically changed my model. See, we call it as a rotation because we are using orthogonal matrix. We call that new factors are rotated version of F because rotation is multiplication by an orthogonal matrix and we are using an orthogonal matrix. But if we can do it with some other matrix, we would stop calling it rotation. What is the problem?
no, ma'am, I didn't understand this. Why it would not be differing? Because orthogonal matrices won't make a change in the actual data, but this H inverse will make a change.
But who told you that you are not? I am not changing data at all. See, X is unaffected. I am changing factors. I am not
Yes,
changing
ma'am.
X.
But the factors would, the weightage would change, right, for each and every factor over here now,
But
for the
that
common
that would
factor.
get changed even by G. In fact, that is the purpose of going for G. That if you get factors which are not interpretable, then you rotate them. So rotation also makes changes in all the things in all the coefficients. We will see in example that rotation does change all the coefficients. Rotation doesn't mean scaling. Okay, I don't know if you guys are getting confused between scaling and rotation. Rotation does not change 1 2 to say 2 4. This is not rotation. Okay, rotation also changes things significantly. So who told you that you shouldn't change things? Because anyway rotation is also changing, so why not through H? Because mathematically, at least up to this stage, I don't see any problem. Of course, there must be some problem. That's why people suggested orthogonal matrix, and I want you to figure out that problem. That is my question. What is the problem if I use arbitrary matrix instead of orthogonal matrix? Anyone?
Ma'am, the does the determinant make the change? Because determinant for orthogonal would be 1 or minus 1.
But why should we be concerned about determinant?
Ma'am, because if the value, again it comes back to the values.
No, see. Okay, you can take this also as a homework. You guys can take this also as a homework. Why not this? Okay, this is also homework. So you have a lot of homework to think about things over weekend. We'll stop here. Is it okay? I agree with you that yes, it should not be HH inverse, but I want a mathematical reason why it won't work. Okay? Think about it. I'm sure at least a few of you will get it. Okay. So let us stop here. Um, about next week, I'll let you know later when would I conduct live lectures or when we would have recorded lectures. Okay. And please try to solve the question bank over weekend. PCA question bank. Okay. Thank you.
Thank you, ma'am.